Hey, Nick.
Hey, how's it going?
Good. So
Good.
I saw your conic sheets here.
Okay.
Yeah, that's got to be helpful
Oh, extremely, yeah. We had the test over it.
on the test. Okay.
hmm
Um, well, I don't, you might need that in front of you. Uh,
Uh, yeah, well, I mean, now we're just doing review for the final.
oh, okay. So we're not necessarily going to do conic sections tonight.
No, no.
What do you got?
Okay, so, these are like, so we got two sheets for practice,
Okay.
and I did as much as I could until I got tripped up, and these are like the problems I was tripped up on, just forgetting how to do some stuff.
Okay.
Okay, so the first one is graph the following rational function and including label all the asymptotes, holes, and intercepts.
Okay.
And the function is y equals x cubed over 2x squared minus 8.
Okay. What's the first step here?
Um, Identify any horizontal asymptote, or vertical, sorry.
Vertical probably is the best one to start with.
Yeah.
Um, And in order to identify the vertical asymptotes, I have to figure out what makes that denominator zero.
hmm And that would be -2 and 2, right?
Correct. So
Oh,
the vertical asymptotes equal x equal plus or minus 2. There's two of them. Okay.
okay.
Now, the horizontal.
This is where I like had trouble.
Well, when the degree in the numerator is exactly one more than the degree in the denominator, you have a slant asymptote. And
Okay.
you get its equation by doing the division.
Okay.
Okay? And uh, let's see how hard it is to do this division here. If it's not so easy to do that division. I think I need a dummy variable here also. So that's what I'm going to divide into x cubed plus 0x squared plus 0x. So let's see. If I divide 2x squared into x cubed, I get 1/2 x. And if I
hmm
multiply that by all three terms, I get x cubed plus 0x squared
Plus four.
minus 4x.
That would be minus 4x.
Okay? And now, subtracting, I end up with 4x.
Do you end up with 4x or -4x? Oh, it's -8. Okay, so it would be 4.
Positive. In other words, it's 0x minus a minus 4x, so I get plus
Yeah.
4x, and that's a remainder. So my remainder is 4x divided by my divisor, and the
hmm
equation of the slant asymptote is that.
Just 1/2 x.
Just the quotient, not counting the remainder.
Okay.
And a lot of times there's a number attached with that would be the y-intercept. But in this case, so my horizontal or my oblique asymptote, whoops, let me draw it proper. It's got a slope of 1/2, not, I was drawing it as if it has a slope of 1. Well, a slope of 1/2 is like this.
Mm-hmm.
A little flatter. And I got my two vertical asymptotes at plus and minus 2. There's the one at plus 2. There's the one at minus 2. And I actually don't need that in between my vertical asymptotes.
You don't need it in between?
I don't think so. Let's think about this now. What all did they want? They wanted vertical. Read again what
they want you to label all the asymptotes, holes, and intercepts.
Okay. Holes come from finding a factor that cancels in the numerator and the denominator.
Okay.
And I don't have one here.
So there's no holes.
No.
Yeah.
In other words, I could factor that and make it equal 2 times x plus 2 times x minus 2. In other words, that's what the bottom factors into. But when I put x cubed on top, I can't cancel anything.
Okay.
Nothing at all. And that's, in other words, if I had, say, an x minus 2 at the top also, and I canceled that and that would give me a hole at x equal 2. But I don't. And what factoring does is it takes what would have been a vertical asymptote and turns it into a hole. You with me?
Yeah.
Okay. So, there's no horizontal asymptote here either. It's an oblique asymptote. You only get horizontal asymptotes when the denominator is greater or equal in degree to the numerator.
Okay.
Okay. What else? Vertical asymptotes, horizontal asymptote, or all asymptotes, which we've got. Holes, which we've done. What else after holes?
Intercepts.
Okay. Intercepts are relatively easy.
Okay.
What's the y? What is the y-intercept going to be?
Wouldn't it be 0?
No, the y-intercept comes when x is equal to 0. So plug in 0. Yes, you're right. It would be 0. What am I thinking? Okay. So the curve goes through that point right there.
Okay.
To get the x-intercepts, well, I can tell I got one of them right there, but now is where you set y equal to 0, and you solve that. And if you have 0 equals a fraction, its numerator has to be 0. So x cubed has to be 0. So the only x-intercept we have is also at the origin. So the origin is both my y and my x-intercepts.
Okay.
What else? Is that all they wanted?
Yeah.
They want
they want you to graph it too.
They want you to graph it. Okay. This thing is hyperbolic in nature. Okay? Which means it looks something like this, most likely. In other words, it's asymptotic to all my asymptotes. And then it does something, usually in between, it either does that or it does this. And it clearly does the second one because we have an x-intercept and a y-intercept at the origin. So in between my vertical asymptotes, it's going to do this. And then that horizontal asymptote that keeps going like that, actually. The other side of the graph, like I said, it's hyperbolic in nature.
Okay, so it's going to reflect
what I mean by that? In other words,
yeah.
Good. Now, I'm not positive I have it in the right quadrants. In other words, it's possible that it could be in these quadrants here. In other words, it might look something like this.
Okay.
And then do
How
what
do you,
it's doing in the middle. And then the other possibility is that it would do that. And,
how would you,
well, here, let me draw what it would look like exactly if it was the other way. It would come down like this. What usually happens here is that when you're on one side of the asymptote, you always come out on the other end. In other words, if I'm going from right to left and I'm going down to negative infinity, it means on the other side of the asymptote, I'm going to come down from positive infinity. So the green makes sense and the red makes sense. Now let's figure out which one is correct.
okay.
Well, what's that point right there?
That would be 2, 1.
Yeah, exactly. 2, 1. Okay. So let's put in 3 for x.
Oh, I see how it's going to
Figure
work.
out whether we're on the red or the green part of the curve.
Okay.
If I put in 3, I get 27 over 18 minus 8, 10.
That's 27 over 10.
Yeah, which is
Oh,
almost 3. So it looks like it's the red. In other words, 3 here, yeah, would be up to about that. So I'm going to go with the red, and I'm trying to figure out if there's a way to figure that out, because it's not always clear, because you have to figure out where that oblique asymptote is as to know whether you're above it or below it. But let's see, the equation of the, I can do it. The equation of the oblique asymptote was y equal 1/2 x, right? So when x is 3, this is at 3/2. Well, our point was at 27/10, which is greater than 3/2, so my red is definitely correct.
oh, okay.
Okay, now let's check. Let me open up Wolfram Alpha and put this thing in there and see what they show.
This program you have is very handy.
It is. It's really a cool calculator. Actually, they call this a knowledge database.
Wow.
Yeah, it'll give you information a lot more than just math. I can ask the population of Russia and it'll give it to me. The bottom was
2x squared minus 8.
minus 8. And that's what it looks like.
Oh, awesome. So to get the behavior of the graph, I should just plug in a point and see whether it's on which side of the graph?
I would. That's the way I've always kind of done it. And it works pretty good. I've always considered, well, that's a little difficult because I don't know where that oblique asymptote is, but I do know where the oblique asymptote is. In other words, I plugged in the point x equal 3, right? Which is out there. Well, I can figure out what the coordinates of that are right there. It's 3/2. So that point right there is 3, 3/2. And when I plugged in 3 into the original function, I got 27 over 10, which means it has to be above this oblique asymptote. So that's why I know it's the red and not the green. You might get the green if you had a negative sign in front of that, like that. If it was negative x cubed, then we'd probably be in the green. Okay. But it's hard to tell by just negative signs. In other words, x plus 1 over x minus 1, I don't know if that is this kind of
graph.
hyperbola or this kind.
Okay.
I can't really tell. It's one of the two.
Yeah.
But I have to test it, and I would plug in a positive point and make sure that I was on this graph instead of this one. And so you can always pick a point and figure out which of the two hyperbolic choices. You usually have a choice with hyperbolic functions. Typically, this one has what I call 6 quadrants, but typically if you have a hyperbola, you're either this way or you're in these quadrants.
Okay.
And it's easy to tell by just plugging in a point.
Yeah, and that's what, okay, and that's how you identify the behavior of your graph.
Yeah, exactly. All right, I guess we finished that. What
Yeah.
next?
Okay, this one is, it says sketch a graph of the equation without using a graph calculator. Use the zeros of the function and the end behavior of the function.
Okay.
And the function is f of x equals negative x squared, parentheses, x minus 1, parentheses, and then another parentheses, x plus 2, parentheses.
Okay. So first of all, where are my zeros?
You have a double zero at 0.
Multiplicity of 2.
You have 1 0 at 1. And you have 1 0 at negative 2. Equals 0.
No, here's my double zero. And I know that the curve is not going to go through the x-axis there. It's going to kiss it.
Oh, okay.
Okay, it only goes through the x-axis if it has an odd multiplicity. So at 1, I know it goes through it, and at negative 2, I know it goes through it.
Okay.
Okay, we're looking at a quartic. So it has 3 zeros, and it's going to do one of two things.
Oh, I think I understand this graph now.
That's one possibility.
Uh-huh.
And the other possibility, it's still got to go through these zeros, and it's still always going to kiss off that one.
Mm-hmm.
So it's either the black or the red, and as all I have to do is analyze the end behavior to figure out which.
And, okay, so if the end, so if the graph is negative, wouldn't the end behavior be negative?
Yes. In other words, to see what's going on the left, whether I'm on the red or the black, plug in negative infinity into this. In other words, this eventually, remember, end behavior only matters the highest degree polynomial, which is going to be negative x to the 4th here, right? If I were to multiply that out, my end term would be negative x to the 4th. Now plug in negative infinity for x. What is f of x going to do?
F of x will become negative?
Yeah.
Or,
Negative infinity.
yeah?
It's the black.
Okay.
It's the black curve. Plug in positive infinity for x.
And it will become negative?
So it's definitely the black.
Oh,
Not
okay.
red. In other words, once I've figured out my zeros and whether it goes through the x-axis or kisses the x-axis, then I really only have two possibilities. And I had drawn the black and the red, and now the end behavior will tell me where it starts from. I guess I could start with end behavior instead of drawing two curves. I don't really need to draw two curves. In other words, if I start this problem out, here, let me back up just a second. Start it out with just the zeros, okay? So I have a 0 there, a 0 there. I go through both of those, and I kiss off the one in the middle. Well, if I look at my end behavior immediately, I know that I got to come up from this side.
Yeah.
Because I know that as x goes to negative infinity, f of x goes to negative infinity. So I immediately can do this.
Okay.
Kiss off that. Go through that.
It has to go through that. All right.
I don't need to draw two curves. This is not like the hyperbolic function where I have a hard time telling which quadrants it's in on a hyperbolic function, but on a function like this, you can start with the end behavior, and that way you don't have to draw two curves and check which one it is.
Yeah.
Is that all I wanted on this, was to graph?
Yeah.
Okay.
Use the zeros function. Yep.
I could put this in Wolfram Alpha, and it would look like this also. I know.
Okay.
What else?
I think it's just, I don't know, I think it's the graphs and the horizontal asymptote, all the asymptotes are kind of what tripped me up.
Okay,
kind of
here, let me
little rest of those.
Let me ask you about horizontal asymptotes given the following functions. If I had x plus 1 over x squared minus 7, what's the horizontal asymptote? There's only three cases.
Isn't the only three cases it can be 0, 1, or...
This is the 0 one. Y equals 0 is the horizontal asymptote when the denominator is the higher degree.
All right.
Okay. If I make the problem this, where
then it equals 1.
Now the horizontal asymptote is the ratio of the coefficients.
Yeah, and that's 2, okay, that's 2 over 2.
2 over 1. Coefficients of the highest degree term. This coefficient's 1, that one's 2, so 2 over 1. In other words, if I had this, let's make that a 3 and this a 2, then the thing would be 3/2, would be the horizontal.
Oh, okay.
So when they're the same, it's just the ratio of the coefficients.
Okay.
When the bottom's bigger, it's always y equals 0. And the only third case is if the numerator is precisely 1 bigger than the denominator. I don't know what happens when the numerator is 2 degrees bigger than the denominator. I'm not real sure what you get, but you don't ever see those problems. The only problem you'll see on a test is where like the last one you gave me, where the numerator was exactly 1 degree higher than the denominator. And notice that division wasn't that easy. That was long division. No, I erased it all.
That's okay. I have it on my paper. I can see it.
Whenever you're doing long division, you have to put dummy variables in both your divisor and your dividend.
Okay.
The only thing you care about is the quotient, not the remainder. Once you get the quotient, you're done. You don't even need to deal with the remainder.
Okay. Okay.
Okay.
Cool.
All right. What else you got?
Okay, so the next problem then is x squared, f of x equals x squared minus x plus 1 over x minus 3.
Okay. Vertical asymptote?
The vertical asymptote would be 3.
X equal 3.
X equals 3, sorry.
And, well, that you might lose points if you just put 3.
I think we will.
The vertical asymptote is a line. So
And
you need the equation of a line.
okay.
Okay. How do we get the horizontal asymptote? There is no horizontal asymptote because the numerator is 1 degree higher than the denominator, which means there's going to be an oblique asymptote. How do we get the equation of that line?
The equation of the horizontal asymptote. We should divide the new.
Yes, the equation of the slant.
Sorry, the slant asymptote.
Slant and oblique mean the same. So
yeah,
don't
divide.
Dummy variables here. Everything's accounted for.
Wait, but I have a question. Is there any way to factor the top out in any manner or no?
Well, if you could factor it, but notice it doesn't factor.
Okay. Yeah, I was just wondering.
In other words, it would be a -1 times a -1, and that doesn't give you that middle term.
Yeah.
So it doesn't factor. If I could pull an x minus 3 out of that, then I would have myself a hole and not a vertical asymptote.
Okay.
Okay. In other words, if I have something like the following, x plus 1 times x minus 1, all divided by x minus 1, well, I do not have a vertical asymptote at 1 because this function is equal to x plus 1. But I still cannot have x be equal to 1. In other words, my domain restriction carries forth even though I factored it away. And that turns into a hole.
Oh, okay.
No vertical asymptote over here. It's just the function x plus 1, which is straight line going through 1. And at 1, I got a little hole like that.
Okay.
That's how I would graph the one on the right. Okay? The one on the left that we're dealing with, we got to do this division. So do this division for me.
Okay, so first you would find out what multiplies to become x squared. So that would just be x.
Okay.
And you put that, yeah. And then that would come out to x squared and negative 3x. Okay. And if you're subtracting that, you would add 3x to the equation. So it would become 2x, and you'd bring down the 1.
Repeat the process.
And if you repeat the process, it would be plus 2.
That's all you need.
That's all you need?
You don't need to go any further. That's the equation of the oblique asymptote. In other words, if I do go further, all I'm going to end up with is a remainder of 7.
Mm-hmm.
So my remainder is 7 divided by x minus 3, but that has nothing to do with the oblique asymptote. It's only the quotient.
Okay.
So as soon as you get a linear quotient, that's the equation of your asymptote. Okay, so if I'm graphing this, I got a vertical asymptote at 3. I got an oblique asymptote that is the equation of that line, and that line goes through the point 2 and has a slope of 1.
Okay.
So there's my grid.
So, wait, so I have a question here. When I'm writing slant asymptote equals, would I write that as y equals x plus 2 because it's the equation of it?
Yes.
Okay.
So the slant asymptote is an equation of a line just like that vertical asymptote or horizontal asymptote is, only y equal x plus 2.
Okay.
Is the equation of the slant asymptote.
Okay.
Now, this one, again, I wonder if there's a way to figure out which quadrants. It's one of two things. It's either...
Oh, what if you could figure out the y-intercept?
That or this. Well,
Yeah.
notice that the y-intercept, let's see. No,
So-
the y-intercept's going to be close on either. I'll tell whether it's below that. I know what that point is, huh? In other words,
Yeah.
I know that that's 0, comma 2. So is all I have to do is plug in 0, and I'll know whether I'm the black or the green.
Okay.
If I plug in 0 into the original function, I get 1 over minus 3.
So isn't that negative 1/3?
So am I on the black or the green?
You are on the black.
Yeah, because the green is clearly, the y-intercept would have to be greater than 2.
Mm-hmm.
If the y-intercept, in other words, the black actually comes down and goes through the y-intercept more like that, the way I've drawn it. Here, let me draw it a little better. So let's see, I know I go through minus 1/3. So this thing approaches that oblique asymptote, comes up and goes thing. Now what's difficult to figure out is that maximum. There is no way to algebraically figure that out.
Okay.
What you can figure out is the only way you can get this is in your calculator. In fact,
Okay.
let me erase the green. If they said to you, what's the range, you would only be able to get it from your calculator. Because notice the range is missing everything between that point and that point.
Yeah.
The range is minus infinity to this point on the y-axis, and that point on the y-axis to positive infinity. The
Okay.
domain is all reals except x equal 3. So the domain
Okay.
is easy, but the range for whenever you have a slant asymptote, these minimums and maximums of your hyperbola are, I don't know the algebraic way to calculate it. You could use calculus, but without calculus, you'd have a hard time calculating it.
Okay.
Impossible, I think. I don't know that there would be a way to calculate it without calculus. With calculus, it's pretty easy. You just take the derivative, find out where the derivative is equal to 0, and that's going to tell you what point, where that occurs on the x-axis, and then you could plug that value in to figure out what y was.
Okay. I have one question. What is the major difference between calculus and algebra?
Calculus is, in 4 words, instantaneous rate of change of a function.
Okay.
If I draw a function, well, let's just take this function here. Okay?
Okay.
If I want to know the rate of change between there and there, I can figure out the average rate of change. That's just rise over run, correct?
Yeah.
But if I want to know the rate of change at this point right here, let's say 4, it's the slope of the tangent line. That's the instantaneous rate of change. And notice why that's so hard to figure out with algebra. The rise is 0 and the run is 0 because it's a point.
Yeah.
Well, when you have 0 over 0, it's not clear what you have. That's calculus. And you have to figure out what that slope of the tangent line is. And you take the derivative of the function, and the derivative gives you the slopes of the tangent line. And notice how these tangent lines change. In other words, up here, the tangent line is negative.
Yeah.
Still negative. And notice what happens when you get to the bottom, the minimum of the function, tangent line is 0. The slope of the tangent line is 0. So if I wanted to know where that point occurs, I would take the derivative of the function, set it equal to 0, and I'll find out. And you can find that point out from algebra because I drew a parabola. But if I draw a function like this, And I want to know where this occurs. Where's that point? Where's that point? And where's that point? And where is this point? What is special about all those points? The slope of the tangent line is 0.
Oh,
And
okay.
what that allows me to do is take a very complicated function. This is it's got 1, 2, 3, 4. This is a 5th degree function. This is a polynomial of degree 5. So it would be very difficult to figure out where these peaks and valleys are. And yet, it's a really practical problem. Let's say I wanted to know where the maximum of this function was between these 2 points.
The maximum.
You clearly see that's the maximum, but how do I find it? And you need calculus. You take the derivative of the function and you examine everywhere where the derivatives are equal to 0, and you'll find this point, this point, this point, and this point. And then calculus tells you whether it's a maximum or a minimum. This down here is a local minimum. That's a local minimum. But that's a maximum, that's a local maximum. By local, I merely mean that it's surrounded by points that are less than the peak point there.
Okay.
That's essentially what calculus is all about, is rate of change and area under the curve. Differential calculus is rate of change. Integral calculus is, do you have any way of figuring out the area under that curve? Without, no. We were never taught the geometry that allows us to figure out the area under that curve. Calculus does. You take take the integral of the function and it gives you the area under the curve. So that's what calculus is instantaneous rate of change is half of it, and the other half is area under the curve. And they don't appear that there's any connection between the two, but they actually are. They're inverse functions of one another. Integration is the inverse function of differentiation. And in fact, the backstory on calculus is really quite interesting. Newton, Sir Isaac Newton, invented differential calculus. And at the same time, Leibniz invented integral calculus. And they both thought they were working in 2 different areas of math completely, because they don't appear to have any relationship with one another. And it was only after about 20 years that mathematicians realized that integral calculus is the inverse of differential, just like a function is the inverse of another function.
Oh, wow.
Yeah, they're that connected. In other words, well, without knowing calculus, it's hard for me to describe it. But if I take the derivative of the integral function, it's equal to the integral of the derivative function.
Oh, wow.
That connected, and it took 20 years. So the discovery or the invention of calculus is credited to both Newton and Leibniz, even though they were working on opposite sides of the same coin. And eventually, mathematicians realized they were the same thing, and then now you just have calculus.
Calculus. Wow.
Calculus allows you to do all kinds of things that they had no way of doing prior to its discovery. But it's mainly about rate of change. Instantaneous rate of change. All right. I could get carried away on calculus and talk about it for hours, but
no worries. I actually like that. I just wonder, like, man, how smart do you have to be to invent like a calculus? Calculus in general.
Truly. I know. Every time I see what they used to do, and they had no calculators or nothing back when they invented it. This was 1700 where they invented it. And in fact, the backstory is even more interesting. Newton had invented differential calculus when he wrote the most important math book of all time.
Did he mean to, or did he not?
Well, no, here's the thing. The Principia Mathematica is the name of his book. And you can ask any mathematician in the world, and they'll say that's the most important book on math ever written. And guess what he didn't put in there? He didn't put calculus in there, even though he hadn't discovered it. You know why? Because he wasn't sure of the math.
Oh, wow.
Calculus involves dividing not by zero, but by numbers that are so close to zero that they're infinitesimally small. And of course, the first law of mathematics from time immemorial is thou shalt not divide by zero. And the process of calculus was so close to dividing by zero that Newton didn't trust it enough and did not include it in the most famous math book of all time. And now they say that calculus is absolutely the most important discovery ever made in math.
Wow.
So he had made the most important discovery, didn't put it into the most important math book ever published. That's how smart Newton was. That's why they say Newton was the greatest mathematician in history.
Oh my gosh.
Yeah.
Wow.
It's pretty phenomenal what he did. Yeah.
That makes just my math, but all I've learned from this moment on just seems puny.
Yeah.
Wow. Wow. Okay, well.
So do you have any other problems?
I have one more, but it's kind of an easy one, so I'm not sure about that one. I kind of have, okay. So I saw something on my test that was kind of interesting.
Okay.
And it was, we were solving a systems algebraically and graphically.
Okay.
And so I remember vividly, one of the systems was x squared plus 3y squared equals 1.
Okay.
And the other system was an ellipse.
That's also an ellipse. Notice. In other words, I've got an x squared and a y squared, and I got different coefficients in front of the x and y.
This one was minus, sorry. I know why, yeah, because I got a hyperbola and an ellipse.
Okay.
This was
so
x squared
minus?
And then the second one was an ellipse, which was x squared plus y squared. But it was x squared over something plus y squared equals 1.
Okay.
And that's the system, I just remember having so much trouble with this problem.
Okay. Let's talk about solving it graphically first.
Okay.
The top one's a hyperbola. It's a horizontal hyperbola. Might look something like this.
Okay.
Bottom one is an ellipse. Horizontal ellipse might look something like that. Almost have to. No, I guess it could be down here and there wouldn't be any points of intersection. But there's 4 possible points of intersection.
Okay.
But there doesn't have to be because my ellipse could be like that. And there's 0 points of intersection.
Okay.
Okay. So graphically, there's any number. In fact, my ellipse could be what it could. Yeah, it could only.
I think what I got on my test was that my ellipse was tangent at 3, 0.
Okay.
And then it intersected at 0, or I don't know if it was 0. It was plus or minus 2, but I think the x coordinate was 1.
Okay, so something like this. You said it was tangent at 3.
Yeah. Mm-hmm.
And if it's not tangent over here, it's going to intersect at 2 different places over there.
Yeah.
Okay. So graphically, if we could just graph both of them, we would see where they intersect. So one way to do it on your calculator, put that in as y sub 1, put that in as y sub 2, figure out the intersection points, you have your answer.
Yeah, okay.
Now let's look at solving it algebraically. Well, I don't know why I can't solve it algebraically by elimination. I'm going to multiply the bottom by 3, which gives me
Okay.
3, 3, 3. Now I'm going to add the two equations. That's going to eliminate the y squared, right?
Yes.
Okay, so I got 1x squared and 3 halves x squared. That's 5 halves x squared equals 4. X squared
Okay.
equals 8 divided by 5. X equals plus or minus the square root of 8/5. So there's definitely an intersection point.
Okay.
Two places on the x-axis. And what is the y value? Take this value, plug it into either equation, and solve for y.
Okay.
And since we're dealing with a y squared, we're going to end up with a plus or minus value on the y also.
Okay.
Let's see, how hard is that? That's not that hard to do. Let's plug it into this first equation. So when I square that, I get 8/5 minus 3y squared equals 1. That means minus 3y squared equals negative 3/5.
Yeah.
Divide both sides by negative 3. I get y squared equals positive 3/15 equals 1/5. Y
So y
equals
equals the
plus or
plus
minus
the
the square
square
root
root.
of 1/5.
Okay.
So it looks like there's 4 intersection points.
Okay. And how would you know which point to put with which?
Yeah, good question. Well, when x is plus square root of 8/5,
Uh-huh.
y is either of those. So here we'll go to plus square root of 8/5. We'll call that right there.
Okay, sure.
And y is at 2 different places. Y is right here, and y is right there.
Okay.
Okay? In other words, when x is positive square root of 8/5, y is both of these. Remember, we're not dealing with a function.
Okay.
Ellipses are not functions, nor are hyperbolas. They don't pass the vertical line test. So it's possible that a single value of x, I have two values for y. And that is what I have here. And then when x is minus square root of 8/5, well, y is still there, and y is still there.
Okay.
Okay? So what this tells me is that I have a hyperbola, goes through both of those points, and I have the ellipse going through both of those points also.
Okay.
Okay? And so
All right.
you get my 4 intersection points, and you just do it one at a time, starting with the first x value, and that first x value produces 2 y values. And the
Okay.
second x value produces the same 2 y values. So I can come up with this graph. So the system that you gave me results in this. If I were to put this into Wolfram Alpha, I would see something like this.
Okay.
And it's at the origin, so this ought to be a really good picture of it. Let's do it.
Because we had one of these on our test, and it was the first time I'd like seen a 3y squared and an x squared equal to 1 without like dividend in it.
So what was the top function? It was
X minus 3y squared.
it was x squared.
Yeah, x squared minus 3y squared
Y squared
equals 1.
equals 1, and if I put a semicolon, it'll graph the next function. What was the next function? It was 1/2 x squared.
I don't remember.
Here, let me back up. I got it. It was x squared over 2 plus y squared equal 1, right? Because I multiplied everything by 3.
Yeah.
X squared over 2 plus y squared equals 1. X squared divided by 2 plus y squared equals 1. Should draw the picture just almost exactly the way I got it. There you go.
Oh, wow. Okay. Huh. Oh, that.
So that's another thing about if you're using Wolfram Alpha to separate y1 from y2 and y3 like your calculator has, just put a semicolon in between the function.
Okay.
And then it gives you both of them.
Oh, cool.
And it also gives us the zeros. There they are.
Oh, wow.
And this is actually what I came up with. I just didn't simplify it. We had 8 over 5. Well, I can pull out a -2 from that.
Okay.
Okay. So this, what you're seeing here, is the same as the square root of 8/5.
Okay. Wow. Oh, cool. Cool. Well, that's the extent of my homework tonight, and that's the extent of what I need to go over.
Sounds good. Let's see. What you got scheduled?
I think Thursday?
Thursday at 5.
Cool.
I will talk to you then, Nicholas.
Okay. Thank you.
Have a good one.
Thank you.
Bye-bye.